Hello, calculus fans! We're going to talk about Newton's law of cooling. This is a physical law, and it states that the rate of cooling, or heating, of an object is proportional to the temperature difference between the object and its surroundings. This is provided that that difference is not too large. The idea is that if you have an object that is very hot compared to the ambient environment, then it's going to cool very quickly. Whereas if the temperature difference is small, then the cooling is not going to be as fast. We're going to let big T be the temperature of the object at time little t. And we're going to let A be the ambient temperature. That's the temperature of the surroundings. You could think of this like the air temperature that our object is cooling in. Now we can formulate Newton's law of cooling as a differential equation. And it looks like this. dt by dt, that's big T at the top, equals K times T minus A. K is a constant. It's our proportionality constant. Now we could solve this as a separable equation. It's not all that difficult. But there's an easier method, which is to make a substitution to let y equals T minus A. Now A is a constant, so y prime is equal to T prime. And so our differential equation really turns into dy by dt equals ky. Well, that's our general exponential growth differential equation. So we can use that formula to get our answer for y. And we're going to see how we do that in the context of a cooling problem. All right, so let's try this as an example. We have a cup of coffee. It's being poured at 75 degrees Celsius. And 10 minutes later, the coffee has cooled down to 70 degrees Celsius. Now the room temperature, which is the ambient temperature, is 25 degrees. We want to know how long does it take to cool down to 40 degrees. Keep in mind, all these degrees, they're measured in Celsius. So A is equal to 25, our ambient temperature. So our differential equation is dt by d little t equals K times T minus 25. Now our initial condition is T of 0 is equal to 75. That comes from the temperature of the coffee when it is first poured. Now we make this substitution to let y be equal to T minus 25, and so we transform everything by saying now that y prime is equal to T prime. Also, the initial y value, well, it's just T minus 25, and the initial temperature was 75, so really we get y is equal to 50. So what y measures now in this problem really is the difference between the coffee and the air temperature. So now we can say that y is a solution of our initial value problem. dy by dt equals ky, and y of 0 is equal to 50. You know, this phrase, initial value problem, is talking about a differential equation with an initial condition. Now, instead of separating variables and integrating and coming up with a solution, the more efficient thing to do is say, well, we've solved this differential equation already. And we know that its solution is y of t is equal to y naught e to the kt. And we know that the initial value of y was equal to 50. That's the initial difference in temperature. Now we're also told that the temperature at 10 minutes is 70. So that means the difference at 10 is 70 minus 25, which is 45. So let's plug all this in. So we'll get 45 is equal to 50 times e to the 10k. And if you do the algebra to solve for k, you'll get 1/10 log of 9/10. This is a negative number. If you plug in a number less than 1 into the log, you get a negative number. And so that's the idea behind the cooling here, is that the rate of change of the temperature is negative. So y of t is equal now to 50 e to the kt. And we've solved for k as being 1/10 log of 9/10. We can put this back into terms of the temperature to get the temperature is equal to 25 plus 50 e to the 1/10 log 9/10 times t. Now the problem really was to determine when the temperature of the coffee reached 40 degrees. So we'll plug that in and solve for t. So 40 is equal to 25 plus 50 e to the 1/10 log of 9/10 t. And now we can just do the algebra to try to solve for t. So subtract 25 from both sides, divide by 50, take a log, and then solve for t. T is approximately 114, and we're measuring our time in minutes here, so it takes about 114 minutes, just under 2 hours, for the coffee to cool to 40 degrees. Okay, that's all for now.